Hey students, as promised, I thought I'd make you some more examples that you can study and hopefully learn from this chapter 31. If you watched the last video, you'll see that I did these three in class and I just made a video on those three, and so hopefully those were educational. Let's do these last three here, and so hopefully somebody will find some usefulness and some educational advantage of those. I will point out, as I've been saying all of these, this whole chapter is based upon Faraday's law, which simply says you make an EMF or an electric field when there is a changing magnetic flux or a changing magnetic field. And so you'll see me probably start every problem along this line. Although I will point out that I don't think chapter 31, although it's short, is an easy chapter by any means, because just doing this math is hard enough and understanding this concept is hard enough, but then it usually then involves a lot of pieces of past chapters, because we got magnetic fields, and so that would be like, chapters 29 and 30 come into play, and then we got electric fields and voltages and currents which come into play, and so all of our chapters kind of come together, and that's what can make these problems a bit challenging. They can even go further back to mechanics, and I think that's what number 50 does. So let's take a look here at number 50. I went ahead and I printed it. Here it says we have a bar of mass M. So looking down here at this picture, of length D, resistance R, slides without friction on a horizontal plane, moving in parallel rails as shown in the figure. A battery maintains a constant EMF here. A battery that maintains a constant EMF is connected between the rails, and a constant magnetic field B is directed perpendicularly to the plane. Assuming that the bar starts from a rest, okay, keep that in mind, show that at time t it is moving with a speed of. All right, so there's some mechanics definitely part of it. And I'll begin with the part related to this particular chapter. Maybe I'll re-derive it. But in class and in the book, we showed that the EMF, we called this a motion EMF, was the magnetic field, the length of the bar, and the velocity of the bar. Now, in this case, for length, it should be a value of dV, to keep that together. So maybe run through this again, since this is kind of the basic work of this particular problem, but hopefully this is what I will come out with. And so I'll start with conceptually. You can see that we got a rectangle here, and so as this bar moves, there is going to be less and less magnetic flux coming out of the screen. We got the little green dots. And so conceptually, we see that there is some mechanism, and in this case, a change of area, due to the changing of, due to the motion, there is a change in area, and that area then represents one component of the flux. And so there is going to be a change in flux. So a change in flux makes an EMF. So let me go ahead and just maybe calculate the magnitude of this EMF. And maybe I should even be a little careful, because this is an induced EMF, not to be the same and confused with this battery. So since they call this E, why don't I call this E sub M for motion? And so this is the EMF induced because this bar is moving. And so really we're going to have a little circuit here that is essentially two different batteries. One that comes from the charges that are in there, and that's the first way to make an electric field. And then the second way of making the electric field is the changing magnetic flux, and that's where the second one is going to come into play. All right, so if I just do a single loop, and I can put a 1 for the n, and of course, since I'm doing absolute value, I'll ignore the negative sign. Then I have a derivative of the flux, and in general, the flux is B dot dA, but as we've seen for a lot of these problems, if we have a nice uniform field, So maybe I need to keep reading, or I did, where he goes, magnetic field. Did it say constant? Yeah, a constant magnetic field. And so I can say, here's my magnetic field. I guess I can leave this as a dA, and then the cosine of 0 degrees or 180 degrees, but again, ignoring the minus sign. And hopefully not going too fast here, but this is just the easiest flux, and so it is just the amount of field times the amount of area. And then the area of this would be its length. Let me call this, say, x. And this d, so this would be x times d. And looking at these, the b doesn't change with time, the d doesn't change with time, but the x does change as it moves. And I keep pointing inward. Why? Yeah, I apologize. I was thinking it was moving inward for some reason, but we really don't know that. It doesn't say which way it moves. It starts from rest, so it's going to kind of move on its own. And so let's have kind of that discussion. But this is the magnetic field times d times the velocity. Okay, and so that's the EMF. And kind of the reason why that's as important is if you start off with your initial condition, you will see that the velocity is 0. So in other words, my circuit, if I think of this as a circuit, just looks like this, where I've got the EMF from the battery, the resistance from the bar, and so what I might call the initial current would be the EMF divided by R. And looking at the polarity here of the battery, it would send the current kind of in a downward direction. And then if I go back a chapter and do L cross B, I put my fingers down, close towards B, and I'd get an initial force outward. And so that answers my question, which way is this bar going to start to move? And it's going to go outward. And so as it moves outward, it does gain some speed. And according to the problem, it should follow this equation. So we've got a lot of work to do to kind of work up to that. But at least I know this much, that the initial pushing the bar outward, is more and more flux. And so it, moves outward, and it looks like if I were to graph this, let's see, velocity versus time, I've got a decreasing exponential that is upside down, offset by 1. And so I would have kind of like a terminal velocity equation here for this velocity. Okay, so keeping that in mind, I'm going to go ahead and do the Lenz's law, which is saying that as this bar is moving out and more flux is coming out towards you, Lenz's law says we oppose the change. That means the current that would be generated just from the induced EMF, not counting this one, but if this bar was just moving out on its own, so in other words, what direction is the EMF from this motion EMF? It would want to make flux, let's see, going in, because as more comes out, it wants to get back to where it was, so it would go in. So I'll take the thumb of my right hand, I will put it down, I will look at my fingers, and that would tell me that it would want to send current in a clockwise direction, or another way of saying the same thing is it is opposing this EMF. It is opposing more current. It'd be kind of weird if it didn't, because then as it moved, it would make a greater voltage that would add to that voltage, and it would just go, spiral out of control, if you will. Kind of be an infinite amount of energy. So it's not a surprise then that after we analyze all of this, we can now think of it as this type of circuit. We have the EMF from the battery itself, the charges. We then have the resistor from the resistance of this bar itself. But because it's moving in a magnetic field, we would then have an induced EMF. And this would be a good way of writing a circuit diagram of what's going on in this problem in terms of electronics here. And so now when I go to say what is the current, I would, in fact, maybe I'll just do a KVL and maybe start here and go clockwise or counterclockwise. I would say E minus IR minus the motion EMF completes the loop. And so solving this for current, I would have the EMF from the battery minus the EMF from the motion divided by the resistance. And this is just Ohm's law for the circuit. These two batteries are competing with each other. They're fighting with each other. And so this is just V divided by R. It makes sense. Okay. And so that is the part, I guess I would say, is related to this chapter. Now, let's add to this, because we need to then put the force, which takes us back to chapter 29. And so the magnetic force, okay, which we've already decided we know what direction it is, or at least we decided the initial. And then you can see that the EMF kind of builds up, reducing the current. In fact, you can kind of see that it's going to build up until the EMF of the motion equals then the EMF from the battery, and the current is now 0. When the current is 0, there is no more force on this moving object. So not, too big of a surprise. In fact, you can see it in their equation that we're asked to prove that as time goes to infinity, this one goes away. And if you move the BD to that side, you can see that the BDV, which is the motion EMF, is equal to the EMF of the battery. So that's conceptually what's going to happen, is this thing's going to just keep picking up a speed, but in kind of an exponential way, because every time it picks up speed, there's a bigger pushback, which is less current, which is less push. But calculating the magnitude of the force, this would be I times the magnitude of L cross B, which would be ILB sine theta. And of course, we'll want to be kind of a little careful here with what symbols we have. But this force, of course, maybe I'll start with the current that's in here, and that's what we did up here. So this would be E minus the motion EMF over R. L is the length of the bar, and so this is where there is this, length of with a current that has a force, and they call that a D. So I'll replace that with a D. There's the magnetic field. And the angle is the angle between the current and the field. And so the current is going down and the field is coming up. And so that's a 90 degrees. And so that's just 1. And that would, of course, equal the force. Now, let's go way back to chapter 5, because Newton's second law says the force must equal to ma. And a, of course, is the derivative of the velocity. And that's how I'm going to get an equation that has velocity in it, which hopefully then I can solve for velocity and come up with what they're asking for, show that the velocity follows this particular pattern. Now, let me kind of keep going here. But maybe I will put the R over to here, and also the B and the D over here, because I then have this E, and then here is a minus, and then now I'm going to put in the EMF that we did for the motion B, D, V. So B, D, and V. And looks like I've got then some calculus to do, so I might need to start numbering my pages here, because I need to now solve this for velocity. And I've got a derivative of velocity here, but I've also got a velocity there. And that's what's going to make it a little more interesting of a challenging problem here. So what I like to do with these problems is put all my V's together and all my T's together. If you can. This is called separation of variables, and not all problems are separable, but the easiest ones are, and this appears to be, it might be kind of a little tricky to get there. Let me just leave the R, the M, the D, and the B alone here. But I'll leave the dV over here on the left-hand side. But I will move the dt to the other side. And that might be the first step. Sadly, it doesn't complete my goal because I still have a v over here. And if I do a distributive property, that kind of mixes the T's and V's again. I don't want that. So let me do a division here. And so I can separate the V's and the T's. And so everything that has a V is really in this little group, and everything that has a T is in this little group. And these are just constants, and I guess they could be on either side. But once you have them separated like this, and like I said, not all differential equations do that, but fortunately this one does, you then just integrate both sides. And so on the velocity side of the equation, let's pick the limits of saying, okay, this object starts with 0 velocity at 0 time. And then instead of saying, let's figure out what the speed is from 0 to 1 second or 0 to 2 seconds or 0 to 3 seconds, let's use the limit as a variable. Let's say 0 to some time t. And then that would correspond to saying from 0 speed to some velocity v. And so when we're all done, we will have an equation that has this as the variable v at some moment in time t. And hopefully it will match this pretty complicated looking equation. And I don't see it quite yet, but I guess I kind of see how it's beginning to pan out. So let's keep going. So the right-hand side I'll do first, because the integral of dt is just t, evaluated from t to 0 is just a t. So that one's kind of nice. And this one over here has a resistance, a mass, a d, a b. And now I have an integral that is set up perfectly for a u sub. In fact, it's such an easy u sub, I probably could save a little time and do this one in my head with more of a guess and check method. Maybe I'll do that. Because if I called this denominator u equals to b minus b dv, this would just be a 1 over u. And so when you integrate it, you would get a natural log of u, and then you would substitute the u back. So we know this is going to come out to be a natural log, but there will be, when you do that, u sub a du equals to a minus b d dv. And so because of that, we would expect getting rid of the dv to a du to have a minus bd involved. And here's where I'll just kind of check this since I didn't do it formally as a substitute. Let me just kind of take the derivative in my head because the derivative should get me back to here. So if I take the derivative, this goes downstairs, perfect. And then the chain rule would put a minus BD in the top, which would cancel that, and so that one would go away, and we'd be left with just that. So perfect. And so there's my integration. Now, let me not forget to put my limits from 0 to v. These are just more constants, so let me just put those together. I'll put the minus with the r and the m over here. I'll put the b squared and d squared over here also. And then when I put in my limits, I would have ln, and this would be EMF BDV, and then minus ln of 0, which, using the property of logarithms and putting in velocity of 0, we would just have ln of e, and then that, since it's minus, we can write that as a quotient with the properties of logarithms. So that equals to t. And of course, now we've got some algebra to do to try to get v by itself. And so I'll take that negative and bring it way over to here and all those constants. So this is a negative b squared d squared t over rm. And of course, ln of e b d v over e. Then I need to get rid of the natural log by raising it to a power of e. So this becomes e to the minus b squared d squared r m t. If I bring this e to the other side, I can save a line there. And now if I switch positions, I can put an e here and bring this over minus e to the e exponential minus b squared d squared rmt equals, and here's my b dv when I bring that one to a plus side. And then finally, for velocity, if I factor out the EMF, I get minus E, or 1 minus E to the minus B squared D squared T over RM, and then divided by a B and a D. So quite a bit of mathematics getting there, but I think I got the same thing. There's the numerator, okay, then minus, and I've got the B squared D squared TRM. Yay! All right. So actually, it wasn't quite as bad as I thought it might be. It was magenta, and I thought this might be more of a challenging one. But I don't want to underestimate it. I guess the big thing is it, really required us to, go not only this chapter, which I guess this chapter is our motion EMF, but then we had to go back to chapter 28 for our circuits, and then we had to go back to chapter 29 for our forces, and we had to go back to chapter 5 for our Newton's second law. And so that's what I was saying at the beginning of this video, that I don't know if the real hard part is Faraday's law, although that's hard enough, or if it's the fact that Faraday's law then incorporates so many of the past pieces that we've got to put together. All right, well, let's try the second one on my list here. How about number 61? 61 says this: a conducting rod of length L. And so I think they're talking about this picture here. Moves with a velocity v parallel right here, to a long wire carrying a constant current of I. The axis of the rod is maintained to be perpendicular to the wire, so here's perpendicular to the wire, with the near end, so the near end right here, a distance r away as shown in the figure. All right. Show that the magnitude of the EMF induced in this rod is given by here. Okay, well, they do talk about there being a motion EMF, and there has to be some kind of change in flux. Couple ways we could do this. We could start from scratch, and maybe that would be best. Or we could start from the scratch, or from the idea that we know what a motion EMF is. But I'll start from scratch. And you can see then that basically I'm going to end up doing the same thing for the motion EMF, and we kind of did that at the start of 50. This one we had a rectangle moving in a uniform field. Here, we don't necessarily have the quote-unquote rectangle, but our field is also not uniform because we are next to a wire which is making the field. And actually, maybe that is part of the challenge here, is to recognize we do have a metal bar that's moving in a magnetic field. They don't show it as simply as in this picture, but you would have to then go back to chapter 30 here and say, okay, let's do right-hand rule number 2 and say, okay, I'm going to grab this wire with my right hand and my thumb's going to be in the direction of the current. And so the magnetic field would be coming out of the paper in this way and going in here. And since this magnetic field is coming from a long wire, and writing down the equation of the magnetic field from a long wire, and it has to do with the distance away that you are from the long wire, you can see here that I'm going to have a field that's a little stronger on this part of the bar compared to this part, or rod, I guess is what they call it. Okay, so why don't I make kind of a little rectangle here. Just so that I can kind of see as this bar is moving. And so it kind of gives me a little bit nicer way of seeing here that, okay, I'm going to be changing some flux. And so as I change that flux, this bar is, of course, moving in. So since they're calling the length of the bar L, I'll stick to that. Why don't I call this dimension of my rectangle the Y? Because if I begin this problem by saying the EMF is minus N times the derivative of the change in the magnetic flux, and I just drop the negative sign to begin with, and I make a single mathematical loop, then the N is a 1. The flux is a little bit harder to mess with, because in the last problem we said, this is the easiest one to do flux because the magnetic field is a constant, and we just bring it in front of the integration sign, and then we have an integral of dA, which is just A. We don't have that this time. So we're going to need to say that the magnetic field is not a constant in space, and therefore when we take its dot product, we have to leave the magnetic field inside of the integral. Of course, once we write it out and what factors make up the magnetic field, those would have factors that are a constant. So we can bring those out in front. And so we will in just a second. But then here's the dA and the cosine of the angle between them. And so, again, looking at this angle between them in this picture, okay, As we said, using our right-hand rule number 2 from chapter 30, the magnetic field is going into the screen. So the area vector is either coming out of the screen or going into the screen. And so we have an angle that we would say is either 0 degrees or 180 degrees. Either way, that's a 1 or a -1. And if we're just doing magnitude, we'll kind of ignore all that. And so I have then this integral that I can adjust a few things. First of all, I don't need to worry there with the cosine of the angle. But these 4 factors don't change in space or in time. So I can move those in terms of calculus out in front of not only the integral of the space, but the derivative of time. Oh, I got to check the current. They said constant current, right? A steady current I, yeah. Okay. And then, of course, I'd be left with this 1 over r. And the r is the distance from the wire. So this would be kind of in this direction. You might call it the x direction, if you will. Okay. Because then the area, being the area of this rectangle, I might divide into strips, since the magnetic field is constant along a strip here. I could then say that the area of one, microscopic area would be the y, how high is this strip, and then this dx, what is the width along here. Okay, mu naught I 2 pi. Because looking closely at this, and maybe I'll start with the y, for every strip I add up, the y is the same value. So the y would be a constant as I'm adding up the space, the strips. However, as the rod moves forward, these y's get smaller, so y changes with time. So I can take this y in front of the integral, but not in front of the time derivative. And so now I just end up with an integral of dx over r. And that's probably a poor notation on my part. In this equation, I was calling the distance away r, and they have a symbol r here. And so I probably really should have called this as my axis x away, because this meant as a variable. This they're saying is a constant. This is some value r. And so I think I would have been better off to have recognized that at the beginning, that they used a symbol r as a constant, whereas over here I was trying to say r is a variable by how far away you are. And that's what I put in here, and that can be confusing. So I should have really probably wrote that as a 1 over x. Yeah, and I think that would look better. And that's obviously some of the challenge of some of these problems is what symbols do we use, especially when we're, doing a problem like this one that has a symbol R, and we jump back to chapter 30 for the magnetic field from a wire, which has an R in it, but they don't have the same meaning. We could end up doing what I just did, which is to have 2 of the same symbols, but meaning something different. And if we don't catch that, we run into troubles. And I'm glad I caught it before I got too far along. Okay, so now actually doing this integral, it looks like the limits of adding up my x would go from r to r plus L. Okay, so mu naught I 2 pi. Maybe I'll leave this alone for just a second. But this then is then the natural log of x evaluated from r to r plus L. And now I think we're actually done. This was not quite as long as I thought. Conceptually, it might, though, be pretty hard. But this I would just interpret as how y changes. That is the velocity. That would take us back to really chapter 2 of this book. What do we mean by motion? What do we mean by velocity? So dy dt can be just interpreted as velocity. And then here, I would just put in the natural log of the upper limit, r plus L, and then minus ln of r, but taking advantage of the property of logarithms, write it as a quotient. And I think I'm there, other than the author does take one more step that I don't know if I always like it. I do see the advantage, but he puts the r's together and gets 1, and then he gets L over R. And sure enough, there it is. There's the EMF created by this type of motion EMF. Obviously, a little more complicated than just the simple one of BdV. BdV is nice. That's what, you have this nice uniform field. And that's why this one comes out a little more complicated. We do have motion in a magnetic field. It's just not a uniform magnetic field. So things come out a little more complicated, and not a surprise since the magnetic field drops off as a 1 over distance. And you're going to talk about the flux. So you're going to integrate this 1 over r becomes a natural log. So kind of makes sense once you kind of see where the natural log is going to come into play during the equation. All right, so there's my second, and then what was that third one here? Number 62 here. So let's try number 62. I thought I printed it up. Oh yeah, it's on the bottom half of 61 here. And it looks actually a little bit like 61 here. Looks like we got a motion EMF. Looks like we've got a wire moving. And so here's my rectangle. And there are some things different. The most significant one is the direction we're moving. Here we moved along with the wire. Looks like this one we're going to move away from the wire. But also we actually have you might call a double movement to our wire. Because if I just treated this part as a bar and this as a bar, I've got 2 bars competing with each other, but one bar is in a stronger field because it's closer to the wire than the other one, and so one wins, and there is a small amount of current. Oh, well, let's just see how this plays out here. Here we have a rectangular loop of dimensions L and W. Moves with a constant velocity, okay, V, so away from the long wire that carries a current of I in the plane as shown. The total resistance in the loop is R. Derive an expression that gives the current in the loop at the instant the near end is at a distance R from the wire. So it looks like as we pull it away, there is going to be some change in flux. Going back to the problem we did earlier and jumping back to chapter 30, taking my right hand and saying, okay, if I imagine grabbing this wire, I can grab it and the field would come out of the screen here, arc around, and go in here. And so there would be a field. And the equation for that field, as we did before, is a mu naught I over 2 pi. And again, let me not make the same mistake and call it an R. Let me call it an X, the distance away. And then I'll just emphasize, we learned it as this equation in chapter 30, where R is the distance away, but they're going to use R for something a little different. They're going to use it as some distance, not where we're trying to get the magnetic field, but where the edge of the rectangular loop is. And so I don't want to use that symbol R here. So I'm going to change it to a symbol X, and so call this the X-axis. Well, like we just did if you watched number 61 a moment ago. Okay, so this would be the magnetic field. And then notice the magnetic field gets weaker as you get further out. So what that would mean is when this rectangle is in close here, there's a lot of flux, and as it goes out, there's less and less and less flux. And so that means there is a change in flux. And that means Faraday law could be applied here, and there would be an induced EMF, which would then make a current. And that's what it says. Find that current, right? Carries a current I, the total resistance. Derive an expression to find the current in the loop. And I think when they also say current, they also mean direction. So let's make sure we deal with direction. But we'll just deal with magnitude here at the beginning. And so going to, I guess, chapter 27, we know that the current is just V over R, Ohm's law. But in this case, that voltage is coming from a motion EMF. And that motion EMF right here is coming from the change in flux of this moving rectangle. And so there's the main thrust of this chapter, chapter 31, Faraday's law. All right, so let me just kind of do like I do with a lot of these. Let me just kind of ignore the negative sign for a moment. Not worry about what direction. Let me just calculate the magnitude of the EMF. And since we're only dealing with a single rectangular loop, this would be nicer if they had like 20 loops or something, so I can put a 20 there. But they don't. They just have a single rectangle. And then the derivative of the flux. And this is where our flux calculation comes out a lot like the one we just did in 61, where I have a rectangle. Now, in this case, the rectangle was closing up and becoming smaller. Here, the rectangle is not closing up. It's moving away. So we'll have to consider that a little differently. But nonetheless, there is a change in flux. And so I'll start by putting in the equation for the magnetic field, which has to do with how far you are from this wire. And so the field would be strongest in the rectangle on the near end and weakest over here. But I'm going to add up a bunch of strips like we did back in 61. And so when I do this dot product, I'm going to think of the dA. So I guess I'm thinking of this as B dA cosine of theta. And so there's the B. The dA is this strip where I have L and I have a dx. And then the angle is either 0 or 100, depending on some definitions you have. And again, irrelevant, then I talk about the magnitude of it. So I'll just kind of drop that off. Okay, and now this is a good time to kind of say, okay, what of these properties, don't change within the rectangle that I'm integrating, so don't change in space, and which ones don't change with time. And I believe the current, in there they said the current carries a current I. Do they say a steady current moves with a constant velocity away, carries a current I in the plane? They could do a little better of saying it's a steady current like they did up here. But I think they are definitely implying that the current is steady. And so the current does not change with space and does not change with time. And so I will move the current calculation in front of both calculus operations. Okay. The L is interesting because the L is this length of it. And so if you're adding up a bunch of strips in this vertical direction, every L is the same, so I can pull it in front of the integral. And as the rectangle moves outward, all the L's stay the same. So I can actually then say the L is also a constant in time, which, by the way, that was what was different back in problem 61. 61, our rectangle was a y, which we said was constant in space, but we did not move it in front of the time derivative because our rectangle was compressing up and getting shorter. Okay, and that's not happening here. So then we just have this integral of x dx with the limits of, well, it's going to start at r and go to r plus w. And so this, and I'll talk about the time derivative here in a second, but this would be the ln of r plus w over r again when we do the integral, take the limits of the integral, and then take the property of logarithms and subtract them. Oh, and actually looking ahead, that's probably a mistake. Normally I like to put them together, but I probably shouldn't this time, and I will explain. Because our last step here is to take the time derivative. And as I look at here, the r does change with time. The w does not. And so if you can picture this rectangle moving outward, the r is getting bigger and bigger and bigger and bigger. The w doesn't change. And so the L and the w are the size of the rectangle. Those remain the same, but the position, the distance the rectangle is away, does change. Which, by the way, on that one, the r did not change. Okay, with time. Okay, so I need to take the derivative of this. And this, by the way it's written right now, does not look like a simple derivative to do, because not only do I have a derivative of a logarithm, then I got a derivative of a quotient when I do the chain rule. So I don't want to mess with a quotient. So I'm going to take advantage of the property of logarithms and undo the quotient and put it back to what I would have gotten had I just done the limits of the integral. And that way I'm taking a derivative of two pieces. And taking a derivative of two pieces added together, or really subtracted, is much easier than a quotient rule. All right, so when I take the derivative of a natural log, I get 1 over that function. But then the chain rule says I get the derivative of the pieces inside. And r changes with time, although the w, the width, does not. So that'd be plus 0. And then the other one would be right here, where I take the derivative of the natural log, which gets 1 over r. And then the chain rule is dr dt. And then this will allow me to take advantage of one of the phrases I haven't got a chance to use in a while. Oh, by the way, I'll just cross out this plus 0. And that is read the math. Because both of these have this dr dt that can be factored out. And what actually does it mean? It means basically, how does this distance get bigger and bigger and bigger? That is the velocity v. That is really what v is. And so this dr dt is the v, and so I can factor it out and put it over there and get 1 over r plus w minus 1 over r. And I don't know then if it's worth taking one more step and getting a common denominator. But this common denominator would be r plus w. And see, in the top, you would have over here an r. You multiply this by r. And then you would then go minus r plus w. And then, of course, not paying any attention to the pluses or the minuses, because that would actually, the r would go away and you'd have a minus w. But I eventually get a mu naught, an I, LV, and then the w here, and dropping the negative here. And then over here I get the 2 pi r plus w. And so that's the magnitude of it. And that's the magnitude of the EMF. So knowing that, we need to come back up here to our part here and say, okay, let's finish the problem then by saying then the current is this EMF divided by the resistance. That was this statement. So I'll just copy all of that. Mu naught I L V W over 2 pi r plus w, and then capital R for resistance. I suppose I'm done, except about direction. Derive an expression that gives the current in the loop at the instant, and its near side is R. So I think I've listed the answer in the things given in the problem. The I, the L, the W, the V, the R, and the capital R, the resistance. And so that looks good. Now, I probably should say something about direction. And this is where the Lenz's law comes into play. And I've kind of made a mess out of my drawing. So let me kind of start here again. But with it moving out, we would be starting with, I'll call it, a significant amount of flux going through this rectangle because we're close to the wire. And then as we get out, we get less and less and less. So Lenz's law says we oppose the change. In other words, we want to go back to what it was before we started moving it. So there was a lot going in, and as it moves out, there's now less. So the current would be set up in such a way to go back to the original. So we need to have current going in such a way that the secondary flux would go in, bringing it back, so that when it gets out to this location here, you would only have a little bit of flux from this wire, but the current would be set up so that there would be enough flux to get back to what it was. And that happens when I put my thumb into the screen, curl my fingers in a clockwise direction. And so the current must be going clockwise. And so I guess the answer is clockwise, going around in that loop. All right, so there it is. Hopefully that was somewhat helpful. Some good hard problems, good review problems also. All right, take care.